So let's take a look at the notes. First example here says find the average rate of change of y with respect to x from 1 to 7. All right, so this is looking for the slope of the secant line. So we're going to go over to 1 and we're going to identify that point. We're also going to go over to 7 and identify that point. All right, so when we look at average rate of change, so our average, what we really want to do is we want to find the function's output at 7, this function's output at 1, over the two inputs in the same order. So that's 7 minus 1. So really this is the slope formula. There's no difference. All right, so on this one we have 5 for both of these. So we had 5 minus 5 over 7 minus 1, which is 6. That's 0 over 6 or 0. All right, so the average rate of change over the interval 1 to 7 is 0. And we have no units, so we don't need to worry about units on this. All right, so in general, the average rate of change, all right, is always going to be f of b minus f of a over b minus a. All right, and that's the average rate of change of f of x over the interval a to b. All right, and that's going to be a general rule. That is our slope. And again, that's the slope of the secant line. So average rate of change is going to correspond to secant line. All right, if we move on to this next one, it's instantaneous rate of change, all right, and tangent lines. So it says estimate the instantaneous rate of change of y with respect to x at x equals 1. So I'm going to go to 1. And this time for instantaneous rate of change, I'm going to try and draw in the best attempt I can at a tangent line. Now, this is not going to be perfect. We're not a computer, and I don't expect like perfection on these. But what I'd want to see on like a test or a quiz is I'd want to see it clear that you're doing a tangent line and that you're not just using 2 points that are close together on the curve itself. All right, so on that tangent line, I clearly have 1 point. Right, so the point I'm going to use on the tangent line is going to be 1, 5. All right, and then I'm going to pick another point. And I usually look for something that's pretty far away from the point we start with, all right, and as close to a nice lattice point as I can so that I can get a pretty decent estimate. All right, so on this one, we're looking at rate instantaneous, all right, and we're going to use those 2 points. So we're going to use the point we knew, which was 1 comma 5, so 5 on top, 1 on bottom, minus, and then we're going to pick the other point up here at the top. So that's at 3, 9. So we're going to have 9 on top and 3 on bottom. If I subtract those, I've got negative 4 on top, 2 on, which is going to be a positive 2. All right, so the instantaneous rate of change, which is also the slope of the tangent line, or later we'll learn as the derivative, all right, at this point is going to be 2. So the slope of this line is 2. All right, now in general, this is a little bit harder to talk about because what we're really doing is we're really trying to squeeze down to 2 points that are so close together. All right, and the way that we do that is a formula that you've actually seen before called the difference quotient. So we're going to have f of x plus some small amount h, all right, minus f of x, and then that's all going to be over h. So when I really look at that, that's just the slope formula. We've got an input of x plus h on the first function, an input of x on the second. So when I subtract those, I just end up with an h. Now, in order to get instantaneous, we actually have to take that h and we have to shrink it down so it's almost non-existent. So limit as h goes to 0. All right. This rule, all right, gives us our instantaneous, right, rate of change at x. All right, so this is a really handy tool to use if we were actually doing this analytically. But right now we're working off a graph, so we can kind of get rid of the limit aspect by just taking another point that's on the tangent line itself. All right, but instantaneous rate of change is really slope at a point. And the way we do that is we pick 2 points on the curve and then we push the 1 point over to the other point so that we have a tangent line instead of a secant line. Right now, with derivatives or instantaneous rate of change, they're often going to ask you questions about tangent lines. So in example 3, it says, based on your answer, what would the equation of the line tangent to the graph at point 1 comma 5 be? So we found out the instantaneous rate of change, or the slope of the tangent line, or the derivative, all right, is 2 when x equals 1. So we know the slope, and I'll call that m right now, all right, at x equals 1 is 2. All right, another way we're going to see that written often is f prime of 1, all right, equals 2. Those two are equivalent. All right, in this, the m is really slope, right? And here it's derivative, and the derivative is the slope of the tangent line. All right, so this asks for a tangent line itself. So we're going to start with point slope form. Y minus y1 equals m times x minus x1. All right, so I'm going to pick the point we know, which is 1, 5. So y minus 5 equals m. We just found the slope of the tangent line was 2 times x minus 1. All right, this is our tangent line equation. Right? And that's the best form. Don't feel like you need to put it in point slope form. We do that a lot in Algebra 1, but it's mainly so that you'll practice that act of putting it into slope intercept form. Now, if I jump to number 4, 4 says find the average rate of change of f of x between those two values. So if we use our average rate of change rule, we're really finding slope. So I'm going to say f of 3 minus f of 1 over 3 minus 1. F of 3 is going to be 3 squared or 9. F of 1 is 1 squared or 1. 3 minus 1 is 2. So 8 over 2, which is 4. Right, so average rate of change, so R average equals 4 in this case. Now, example 5 is kind of one of the key examples here. It says find the instantaneous rate of change of f of x equals root x at x equals 2. All right, so we're going to take this and we're going to look at it from a limit perspective. So I'm going to come over here and we're going to look at the limit as h goes to 0 of square root of x plus h minus square root of x all over h. So again, that's the slope formula from the input x plus h to x. And we're letting that gap between them, so the change in x, drop to 0 with a limit. All right, so when I look at this one almost screams at me, use conjugates method from our limit days. So I'm going to go ahead and multiply top and bottom by x plus h plus root x, all right, over root x plus h plus root x. All right, so I've got limit h goes to 0. In the top, I've got my difference of two squares pattern, so I've got x plus h minus x. In bottom, I don't, so I'm going to leave that not multiplied out. It'll be easier for us. All right, in the top, that simplifies to an h because the x's do cancel. All right, at that point, the h in the top and the h at the bottom cancel. So I'm at limit as h goes to 0 of 1 over root x plus h plus root x. All right, and at this point, I can go ahead and use direct substitution. When I put 0 in for h, I get 1 over root x plus root x, which equals 1 over 2 root x. All right, and in general, that's going to give me the slope of the tangent line. So this asks specifically at 2. All right, so if in general the slope of the tangent line or the derivative is 1 over 2 root x, right, then specifically the tangent line or the derivative at x equals 2 is going to equal 1 over 2 root 2. Right, you could rationalize that, but you really don't need to. All right, so our instantaneous rate of change at x equals 2 in this function is 1 over 2 root 2. Right, now they're going to ask you a multitude of types of questions relating to that, but that's really the meat of the section right there. So I'm going to go ahead and stop this video with that, and then I will come back and do another video that deals with some of these examples that use those facts.